Hello and welcome to the BEML programming series where we're building firmware for a cortex-m STM32 microcontroller. Today it's episode 14 and well, it's a really important day. This is the day we're going to build the signed firmware mechanism. This is actually what we've been building up to this whole time, and although we've already hit some major milestones, this will be the first kind of summit in our adventurous journey into the world of firmware. So essentially what we are going to do today, if all goes well, is to actually build a firmware signing application that you can think of as being our factory program. Like we take our firmware that gets built, we sign it, and then that firmware can be put on a download page or something and someone can download it and flash it to the device using the firmware updater program. So we're going to have to write a whole new piece of software for that. We're going to have to adapt our firmware update program, and of course we're going to have to adapt our bootloader to be able to deal with this. So let's take a look at the plan for today, because we've got a lot to do. So let's just get started. Alright, so before I do that, let me open up this little preview window for myself, because that will help. Alright. Okay, so here's the plan. Signed firmware mechanism. The goal of today is to build a firmware signer application which uses a secret key and the AES CBC-MAC algorithm to generate a signature, in quotes, and inject it into the firmware. And then of course we're going to implement the verification mechanism within the bootloader and only run authenticated firmware. Now, you need to have watched the previous episode. I think it's fair to say that this won't make a whole lot of sense today if you haven't seen episode 13. So go and check that out. That is a theoretical introduction to AES and cryptography, kind of like real fast crash course in the mechanism that we are actually going to use for this. And that will also explain why signature is kind of in quotes there, because if we want to, like, now we know a bit about cryptography, we can also address the fact that, signature is actually technically within cryptography, signature refers to something slightly different to this, a different kind of encryption and a family of encryption algorithms. What we are technically doing is implementing a MAC, a message authentication code. But they amount to effectively the same thing, the only difference being that we have to store our secret key on the device. So that is a security risk, of course, if your firmware was able to be extracted, which right now it will definitely be able to be. We're going to have to do a bit more work to get it to extraction free. But even then, even with the extraction free mechanisms on, there are still ways to dump the firmware. So it's not the most secure way. But it is what we're going to do today, and maybe in the future we'll revisit some of those more advanced public key cryptography mechanisms, and we'll look at that. But I'm super excited to get going with this. So all the disclaimers that I mentioned in the previous episode still apply today. So truly you should go and watch it, because if you just watch this and you don't adhere to my disclaimers, you're completely on your own. Like, I don't want to hear from you, right? I don't want to hear anything from you if you haven't looked at those disclaimers. All right, so we're not going to write AES from scratch today. No. We are instead going to make use of an implementation that I already have, right? That I've written, and I wrote a whole blog post about more than a year ago. So that's going to be this AESC project. So if we scoot over to GitHub here, here's the article again. I'll make sure there's a link to this in the description. And here, I've even, I have it linked here, but I have it open. AESC. So literally AES in C. It's got its own set of warnings, don't use in production. And that it could be vulnerable to side channel attacks. That's kind of a nod to the future. But yeah, this basically implements a bunch of stuff. We're not going to take this whole project. We just need two files from here. So there's a header file that I want to take. That's aes.h. So you can see here, this is kind of the set of functions for AES. We actually only need a couple of these functions. We don't need all of them. And we'll only be running one of them actually, effectively, or two of them. But like the rest are all kind of exposed as public, although they're kind of like private functions. So we're just going to take the whole thing, it's fine, and we'll scoot back over to the code. And I'll just, before we get started on anything else, I'm just going to go and drop them in to the bootloader. They don't need to live anywhere else. So this is going to be aes.h, and here it is. That's the aes.h file. Okay, and let's go and grab aes.c, which is the corresponding C implementation of this. That's here, and we will just copy all of those and bring them back to a file called aes.c. Drop those in. Great. All right. And yeah, I'm not going to spend too much time kind of on this part. Suffice to say that actually this just contains all of those operations we looked at, right? This is a Galois field multiplication of two integers. And this is a commented implementation of the algorithm that goes into computing that multiplication and doing the kind of the checking this like irreducible polynomial, doing the division, the long division there, and getting the thing. So this is kind of a computational approach to doing that, and the algorithm is explained here. And yeah, this probably won't make sense if you just read it, but I would even download the code, play around, try to get a sense of how this is working if you really want to understand what's going on here. So yeah, we've got Galois field adding a word, which is just XORing the components. We've got our S boxes here, which are literally just constant arrays of data. So we've got one for encrypting, one for decrypting. We don't need any of the decryption stuff. There's also references to specification pages. So if you go and find the AES specification, you can find where this is linked to. We've got the round constant columns, which are added in. So these are all just what we looked at previously. We've got a function to compute the key schedule. So we pass in a secret key and we get out a point, like, well, we need to provide a pointer to a block of memory for the keys, and they're going to, basically this function writes out those keys using this key schedule algorithm that we looked at last time. We got all the functions for doing things like rotating words, substituting bytes, substituting words, shifting rows, doing the inverse of those operations. This is the AES mixed columns function that we looked at. This is the big matrix multiplication. This even looks like a matrix multiplication. All of this stuff, by the way, can be done way more efficiently. Like this implementation, and it says this in the README of the GitHub as well, this implementation is like the most literal translation of the AES specification to code, right? If you actually want to do this more efficiently, well, on some platforms, there's literally a processor instruction that will do all of this stuff, right? From like you give it a key and you run the instruction and like it encrypts the whole block. Like it does all of these things in a single instruction. On x86 machines, you will generally find that. Of course, on these little cortex-m chips, there's no such thing. There are sometimes peripherals for doing AES. So sometimes you can do like defer this stuff to the hardware. But yeah, so this is just like, this is not the efficient way of doing it. Even like if you go like literally, there are more kind of efficient ways of doing this. But this is fine, it works. Adding the round key. And finally, we got a function that does the actual encryption. So that just basically, you pass in the state, you pass in your key schedule, and it just basically does the whole algorithm. Up to and including, you know, not doing the final mixed columns and all of that kind of stuff. And then we have a decrypt, which we're not going to use. So all of the stuff related to decryption or inverse of an operation, we don't need it. We also don't need the S box for the decryption. I'm just going to leave all of it in because the compiler is going to take that stuff out for us anyway. Alright, so now we've copied those in. Let's go back to the plan for a minute, because kind of there are three like major parts to what we're going to do, I think. The first part is like we kind of need to get everything kind of set up in the right way. So that is, we're going to need to fiddle about with the linker script a little bit. So we're gonna have a new piece of information that we're going to plug into the that we're going to want to have in a specific memory location. So of course, like 2 videos ago, we implemented just a kind of integrity check, like using a hash, using a CRC32. So we're going to have a similar kind of mechanism here, where we're going to include a specific, like in the firmware info, include a specific section of data for the key, or sorry, rather for the MAC in the firmware. But it's not going to live directly in this firmware info section. We're going to have a firmware info section and then a section for the key. So we'll take a look at that, and we're going to have to do some alignment stuff. So we'll get into that. Then we're going to have the signing program, and I think we'll tackle this first. So, well, this looks at the steps we'll do for that. And then we have the validation process. That's the bootloader. So let's start with this. Let's take a look at the firmware info struct that we have, and kind of the related information here. So we have this idea that we have a sentinel, a device ID, a version, and a length. And then we had all of this reserve stuff, and then a CRC32. What I'm going to do for now, because we've illustrated the point about having reserved fields and all of that kind of stuff, I'm just going to remove everything else from the length onwards, and we're just going to have this information. Now, I think a better way of doing this would be to do something like this, to add a single reserved section afterwards, and have that set aside 4 32-bit words for that. So you have 128 bits to do what you will. Twice as much space as is used here. And I want to make sure that this structure comes out to be a multiple of 16 bytes, because that will just make some of the calculation that we're going to do today a little bit easier. But today I think we'll also just remove this reserved section. You can imagine that we would have it in there. It would be useful to have it in there, but I think it's just going to be easier to take it out for now. So this is going to be our new firmware info section. And this stuff is probably still, for the most part, okay. I think we're going to need to change a couple of things here. But let's actually go to the application part first and open up the info, and we can get rid of these fields here. And so what we're going to be doing now in the firmware signing program is, well, we're going to be filling in, either in the signing program or the update. I think in the signing program we're going to fill in this version and this length, and we're also going to want to have a signature section. So we'll call it the firmware signature section, and we'll just make sure that this is going to be a UART firmware signature, and that's going to consist of 16 bytes, and we'll just set those all to 0 for now. They don't have to be anything special. So this is going to be the AES key size, and let's in the AES.h, let's just add a define here for AES AES block size, and let's just set this out to be 16, because we could use we have a structure in here, right? We have some type definitions. So we have the idea of an AES column, which is just an array of 4 UARTs. So that's a column. And then we have the idea of an AES block, and that's just 4 AES columns. So this is literally just a 2-dimensional matrix of 4 by 4. Very literal translation of the blocks that we looked at in the diagrams. So we can use these types, and we could do something like size of AES block T everywhere, but I think that's a little bit annoying. So instead, we'll just use AES block size. And of course, block size can vary in AES, but we're going to use this 128-bit version with 11 rounds. Okay, so now we can include that. We'll include AES.h, and we'll make that AES block size. Okay, great. So now let's go to the linker script and let's make sure that we've got something that makes sense for this section now. So linker script. All right. So what do we have? We've got our bootloader section, then we have our vectors, we have the firmware info section, and we want to make sure that that's still there. What we also want to have is the firmware signature after that. And one more thing we're going to want to do is we're going to want to, for our own sanity, just to make life easier, we're going to want to align these structures to 16 bytes. So what that means is that, normally when the linker is putting everything into memory, it's going to take like, okay, I've got this section, it's, 100 bytes, I put it here. Oh, I've got this other section I need to plug. Okay, I'm going to put it directly after this last thing. And what we're saying instead is like, wait, no, instead of making it on the 100 byte mark, let's instead make it to the next multiple of 16. So like figure out what that's going to be and put it at that address instead. And then just leave that space in between, leave it as kind of a padded area. So we do that sometimes just to make sure addresses are in a convenient way. Sometimes you do it because your instructions need to be on a particular boundary, often a 4-byte boundary. In this case, we just want to make sure that as we're going through and doing the AES CBC, that everything is just on a nice, neat 16-byte boundary. And we know that where this thing starts is on a 16-byte boundary. And we know that the next thing over here is going to be on a 16-byte boundary. So the way we can do that is literally like this. So we're going to come up here to the vectors and we will just modify this to align to a 16-byte boundary. Great, that's what we're doing there. So that should be enough. We should end up with the signature part inside. I'm just going to compile this, include AES, no such directory. Okay, yeah, of course, we don't have that in the app, so sorry, we'll go back to the constant. All right, let's just make sure that we have that section inside, so we didn't lose it. And if we go to the info, I don't see it having discarded anything, and we should see firmware signature. Yeah, that made it in. Great. And what you'll see, right, is that our firmware signature is 16 bytes, and now our firmware info is also 16 bytes. So that's really convenient. Okay, so what we will need to change here then is that when we go to validate when we're going to work out where we're going to validate from, that's going to be the firmware info address. And the firmware info address is the main app start address plus the size of the vector table. But now it's no longer just the size of the vector table. There's some padding afterwards, potentially, right? If the vector table doesn't line up on a 16-byte boundary, there's some padding. So what we actually need to do at this point is we need to align this part as well. And this is tricky. You'll find this in like any C code base of any significant complexity. You'll find this macro basically. And this macro, it takes in an address and an alignment, and it kind of does this little calculation on it. And yeah, so what this will do is it will do exactly the same calculation that the linker script is doing. So what we can do here is we can say that the firmware info address is aligned to a 16-byte boundary. And let's put that whole thing in brackets. We don't need to, but I'm going to do it just for the sake of it. Okay, and like I don't want to leave this kind of magic on the table, so let's actually quickly just go through what this looks like. So what we're doing here is, let's imagine our address is, I don't know, 000000005. Let's imagine this is the address, and we want to go to a 16-byte boundary, just like we're trying to do now. So what this address should be is it should bump itself up to 16, right? That should be the result of this. Maybe we can use 15, hex 15 instead, as that is a little bit, that will do. So we would expect in this case it will bump up to hex 20. It will go to the next kind of boundary of this 16-byte. So what's going on here is we're taking the address and we're subtracting 1, and then we're adding the alignment. So this is what the calculation we're doing. So in that sense, what we come out with is 0x00014 with the -1, and then plus this hex 10, we get 24 hex. Okay? And then we're going to take that value and we're going to mask it with negative alignment. So our alignment, if we think about it as a 32-bit integer, is now this. And if we go for the negative alignment, basically what we're doing is we're like, it's 2's complement. So we're like flipping around a whole bunch of bits. The way that you get the 2's complement version of a number is that you invert the bits and you add 1. So if we invert the bits here, well, obviously all of these zeros, they go to F. So let's just change those over, F. And the 1, well, if you imagine 1 is 0001, that's going to become instead 1110, and that's hex E. And then if we add 1 to this, because you need to flip the bits and add 1, well, that is going to bring us to hex F0. So effectively, this is what this does for our computation. So in the end, we take this hex 24, we mask it with this value, and that comes out to be, of course, we drop the 4 on the end here because we have a 0, and we end up with this. Alright, so that is how we do this address alignment. There's no magic going on here. This is just some little bit of bit manipulation, masking to get things up into the right way of doing it. Alright, so that's how that works. Now we've got the right firmware address. We should validate from the right place, and we're still going to have the right kind of validation length. Although validation length, actually, you know what? The worst part about this is that we don't need to do these parts anymore, because one of the drawbacks of what we were doing before with CRC is we were validating everything after the firmware section. I called that out, right? I said that this is not the best way because the interrupt vector table is not being taken into account, right? So if we were to have some corruption on the interrupt vector table, we would miss that completely. That was just to make life a little bit easier. We're not going to make life easier in this episode, so we're going to get rid of these. And instead, so now we've got the idea of the firmware address, but let's also have the signature address as well. So signature address, that is just the firmware address plus, and again, we don't have access to that AES header here, so we'll just make it plus 16. Oh no, I guess we can do here, we can do the size of the firmware info struct, which in this case happens to be 16, and will always be a multiple of 16. That's a constraint we're saying, but in this case it is 16. Alright, so that is everything we need to do here, I think. Yeah, so we've got our vector table aligned, we've got the firmware info as a multiple of 16 bytes. We don't have the CRC anymore, we don't need it. The AES CBC-MAC is effectively going to function as a hash for us, and we're going to compare that, and if it doesn't match, then we're not going to jump to the firmware. So if there was an integrity problem, we would catch that in the CBC-MAC as well. And then we have a signature section. Okay, so let's go about writing the signing program. So let's make a folder here, firmware signer. And let's mix it up. Let's write this in Python. Why not? So this is going to be, I'm just going to make it main.py. Okay, so let's copy this a little bit into here, and we'll just comment it out. So what we're going to be doing here is creating a temporary firmware image that removes the bootloader. So keep in mind, of course, when we build a firmware image, right, firmware.bin, it contains the bootloader. We don't want to distribute the bootloader because the bootloader contains our secret key. So we definitely don't want to like put that into everyone's hands with a firmware update. That would be a little bit too easy. No, instead we're going to create a temporary firmware image and zero out the signature section. Yeah, of course, the signature section is already zeroed out, but I wrote that here for some reason. Then we are going to kind of store away the firmware info section. Well, actually what we're going to do is we're going to build a temporary version of the firmware info, the whole firmware image. Because if you think about how the firmware is laid out, actually I've got a better diagram for this, of course. So if you think about how the firmware is laid out, it's basically like this, right? We have an interrupt vector table, then we have code and data. Well, actually what we have now is we have the firmware info, and we also have a signature. So this is kind of actually how things are set up right now. We have this section, this section, this section, and this section, and a whole bunch of code here. What we need to do for AES CBC-MAC is we need to somehow make sure that the first thing that we plug into this algorithm is a block that contains the length of the firmware. And that's to prevent against a specific kind of attack that can take place if you don't encode the length. Like basically by having released multiple firmware updates, all using the same signing key and having released the MAC for all of those. If you don't have the length in the first block, basically people can take your multiple multiple kind of signed firmware releases and extract information out of it in such a way that they can manipulate their own firmware update that changes kind of the length of that kind of adds stuff on to the end of an update to kind of sneak extra stuff in without affecting the MAC. So that kind of stuff we want to prevent, so we're going to try to make sure that that length is in the first block that we actually use as our plain text. So instead of just kind of stuffing this into the algorithm, instead we're going to kind of rearrange it. So what we're going to do is we're going to say, okay, we'll do the firmware info first. So we'll put that kind of up here. We don't really need to do the signature because that's not part of the calculation, so we'll just take that out. And instead, this will be the thing that we sign. So it'll be the firmware info, the interrupt vector table, then all the code and data. So we need to shuffle stuff around a bit, and that's kind of the first thing we will do in this Python program. We will kind of extract out the info section as the first block to be encrypted, and we'll kind of put like rearrange like the whole binary image, and like that's what we'll actually plug in. Then we'll use AES-CBC with a zeroed IV to encrypt every block of the firmware. And again, we use the zero IV because there is an attack that can take place where someone can manipulate the first block of input, especially the length section, right? That could be something they could do if you have an IV that changes with every update. So we don't do that. If this stuff doesn't make sense to you, you probably didn't watch the previous episode, you should go and watch that. Okay, so then we take the final block of output from that. That's our signature, that's the MAC. So we extract that, and in order to do the computation of the AES, I'm not going to implement AES here in Python. Instead, we're just going to shell out to the OpenSSL program, which has a whole bunch of encryption algorithms built into it, and we can just ask it to do this for us. So we can actually ask OpenSSL to encrypt, using AES 128 CBC, no salt value, here's our key, here's our IV, here's the input file, and here's the output file. So we're gonna push that work of doing the actual first layer of signing to a different program. We could implement it ourselves, right? We could download the AES.c project that I have, and we could use that instead. But this is much easier, actually. And we're going to implement the whole thing in the firmware anyway. So, okay, all right. So then we're going to patch that info back into the original firmware image and account for the padded length of the encoded firmware. So the encoded firmware has a padded length, potentially. So if you don't have a multiple of 16 bytes, the length of the last block is padded. And actually, if you have exactly 16 bytes, it's still padded, but then with a whole additional block. So we'll see how that works. All right, let's start writing this program. Okay. I want to have this basically take in an argument like the firmware we're going to sign, and maybe also a version number, and we'll use that information to do all of this stuff. Like in the firmware update we have now, we don't take any arguments. I want to change that today. So the first thing we can do is check some imports. We'll need sys, we will need OS, we will need subprocess, not submodule, and we will need path, probably. No, that's part of OS. Maybe this is all we need for now. If we have something else, then we can check that. sys.argv, and if that is less than, is it 2 or 3? I always forget, it's different in Node. I think it's 2 in Python. Then we will print an error message, which will be usage firmware signer.py. This will be our input file and version number hex. Okay, so I guess we do need 3 arguments. And then we will exit with exit code 1. So that will just take care of that for us. Just check that quickly before we get into it. So we should be able to run Python firmware signer main. So then if we give it some file here. Okay, good, all good. Okay, so then let's read the firmware file. So with open sys argv 1, I'm going to read that as a binary file. We will say that the firmware image is f.read, and from this point we can actually chop off the bootloader already, because like this firmware image, we expect that this is like the raw firmware image that we get from the build. So at this point we're going to chop off the firmware, the bootloader. So let's have bootloader size be hex 8000, and we will read from that point. So this is our offset, I believe, or wait, maybe that's not how we do that here. We need to fseek to the bootloader size. Yeah, that's right. Okay. All right. So now we have a firmware image that has the bootloader removed. The first thing we can do is to extract the signature section, or we'll cut out the signature section and read the info. So let's just see actually where the firmware info section lands in the application now, because we've potentially moved its address. So in the firmware updater program, we knew that the vector table size was 1AC, so we can check if that's still the case. I don't think it is going to be the case because that isn't a multiple of 16. So bewitched app firmware.bin, firmware.i, firmware.bin, then we can jump down to 8000 and we can just scroll down and see that the beginning of this is now 1B0. So instead of 1A0, now this becomes 1B0, 1AC, now it's 1B0. And you can see that this is nice because the this lands cleanly on this like nice 16-byte boundary, right? All of these are 16 bytes and we land on a clean 16-byte boundary. This is where the signature is. So we know that the firmware info section is always going to be at this offset. So that's good. We could also read this out of like the ELF file directly. There are ways to just like extract all the symbols and the values that are attached to those symbols from an ELF file. So we could do that in a like kind of smarter way, and especially in Python, there's a really like good standard ELF parsing library that you can use just to extract that kind of information. But we won't do it for now. So that is, let's just copy this into the Python program. All right, good. The other one we're going to need is C types, because we're going to be dealing with byte arrays, and we're going to want to write like larger values into byte arrays and use the C types for that. So that is something we'll take a look at. Okay, so we can say that the firmware info section, that is taking our firmware image and reading. We want to read from everything from this point to this point plus the size of an AES block. Which is of course 16. I think that should work. Let's actually print that out just to make sure. Firmware info section. So let's run Python firmware signer main, and we'll run this on app. We'll run it on app firmware.bin. And of course we need to provide a version number. Yeah, that looks right. Good. So we got that. And then the signing image, well, that's going to be the firmware image. Everything from 0 up until vector table size. That should give us like the vector table, and then we skip the firmware info section. So then we're going to want to add to that everything from everything from this vector table size. Let's call this the firmware info address instead. It's kind of a better name in the end, right? So everything firmware image, everything before the firmware address, and then we want everything from the firmware address plus the AES block size times 2 onwards. So this should be our signing image. So what we've done there effectively is to, oh no, of course we don't want to remove that. Yeah, so this is the, we don't really need to extract this. What we need to do is to say that it looks like this. So the signing image is the firmware image, first just the this part, then we want the interrupt vector table, then we want everything else. And let's write this to a file and make sure this looks right. Open firmware to be signed.bin. Write that as a binary. f.write signing image f.close. Let's try that, and let's take a little look at that. So we've got our our info section here. Then this looks like the vector table, and that should, yep, that looks about right because it's of size 1b0, but we're skipping this first one, so we get down to 1c0, and then this should be, this stuff should be the actual code, and we can check that quickly. We can check that quickly here. Do the same thing. How do we do this? Go to 8000. So the code, the first part of the code should be 38B54F. And what we see on this one is 38B54F. Yeah, it's good. All right. And then the last byte should be 24F400. And then here, just to make sure we should get everything, but just to make sure, scroll all the way down. Yeah, great. So that's literally the image we want to sign. That looks brilliant. So yeah, that's perfect. We can actually write this file. So let's do that. Let's have this be the signing image file name. It's going to be firmware to, or let's call it image to sign. Let's delete this one. You can actually delete both of these firmware images here. Alright, so then we will write that out. So I should have just left it there. With open this one, write binary as f.write. Of course, we could use like a proper temporary file API for this, but I want to be able to go in and check things as we're going. So in the end, we'll, like, after we've done all of this, we'll do os.remove to remove these files. But we'll leave it for now. I just want to check that everything is working correctly. Okay, then we can actually run this command from OpenSSL. So let's do that. The OpenSSL command is going to be like this. Python f string, and the key, yeah, we'll need to put a key in here. So what's our key going to be? Let's make this signing it's going to take this as a string. So let's just make our secret key something really straightforward. 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Here we have 32 characters. Yep, so this will be our signing key. It's not like, this is not an actual secret key, right? This is an example key, so don't worry. I just want something that's really easy and recognizable. So that will be our signing key. And in our OpenSSL command, now we can replace this part with signing key. And our IV, yeah, let's just call it zeroed IV. Uh, 8, 16, 2. So then we can use zeroed IV. Our input file is the signing image here, and the output file, let's make that the this is going to be the encrypted file name. Yeah, let's do it like that. Encrypted firmware image.bin, or just encrypted image. It's not quite the signature yet, it's not the MAC yet, because that is just the last 16 bytes. It's going to be that. So this is the command we're going to run, so let's run that. We can do that with subprocess.call, and we will call this command. But actually, in Python, I think we need to, annoyingly, we need to split these on the space. So it's this split space, and well, let's see what this, if this even works. So let's just run it. It's going to produce some output. Object is required, not string. So we try to signing image file name. Yeah, that's not what we want to put in here. We want to put the signed image in. Run that again. Okay, there's no output, but we do get an encrypted image. And that looks pretty much like, from my quick glance, that looks like random gibberish. You can see that this one is aligned on a 16-byte boundary, so that makes some sense. If we look here at the output, so the image to be signed ends up being 3,468 bytes, and the encrypted image is 3,472. So you see that it's offset by 4 bytes. And I think if we were to take this mod 16, this mod 16, 12, and we have to add 4 bytes to get to a multiple of 16, and that's why there's a 4-byte difference of those. Alright, so that actually looks about right. We don't actually have to do any kind of like telling it to redirect output, because it doesn't give us any debug output. It just is that, so that's good. And then we need to extract just the last 16 bytes, which is going to be our MAC. So let's call it, yeah, let's call it the signature for now. So that's going to be signature, and that is just going to be the result of reading that file. So with, let's do f.close here, and then let's borrow this. So with open the encrypted file name as a binary, we don't need to seek, and this is going to be our signature. Alright, then we can print signed firmware version. We do need to deal with the version, so let's take a look at that in a second. And we also need to deal with the length of the firmware. Yeah. So the signature isn't quite right yet. So let's just put this into place first. Well, this is just going to be sys.argv 3, 2. So the file name is 1. This needs to be an F string. Signed firmware version. And then we can have key equals, and then this is just our signing key. And to get the signature text, 4 byte in signature, signature text plus equals an F string, which is just the byte O2X. And it just formats that as a two-digit hex character. Signature. Alright, but before we actually do this, we need to inject these values correctly. So we've read the firmware image, and let's actually inject these values correctly into that section before we do this. So firmware image, well, let's also first get the version, version, let's do it like that. I'm not even going to check that this is correctly formatted. I'm going to just fail out if it doesn't work correctly for now. So to get the version hex, what we actually need to do is to get the actual value, the version value, we need to pass this to an integer, and we're going to provide a certain base. So it's just going to be version hex with base equals 16. Okay, and then we can write that into the signing, or the firmware image rather. So the firmware image, and this is going to be, let's find the right offset. So this is going to be firmware info length offset. The length offset is firmware info h. So the length is, this is 0, this is 4, this is 8, and this one is at 12. So the firmware length offset is at 8, and is that right? Version is at 8 and length is at 12. So length is at 12, version is at 8. Yes, and then we will write that into this section, and I need to try to remember how this works. So C types, it's going to be a C UART 32 with a certain value, but we want to encode this as little endian. And oh wait, no, we don't want to use C types. We probably could use C types, but what I actually want to do is to use struct pack. So we want to use struct dot pack into, and we want to pack. And I need to remember what the struct packing keywords are here. I'm not going to be able to remember that. So I'm going to peek. How do we do that again? I'm coming up empty on this. Oh yeah, okay. Pack into and then less than I. Okay, so this is the magic incantation. So this says it's little endian. This says it's a 32-bit signed integer or unsigned integer. I think this is unsigned integer. And we're going to write the length field. So we are going to pack into the firmware image buffer at the offset, and that's going to be firmware info address. No, address is not correct. This is also an offset. So that's the offset, and we're going to pack into the firmware info offset plus the firmware info length offset, and we're going to write the length of the firmware image, and then we're going to do the same thing but into the version offset, and that's going to be the version value. Okay, I think I've done that correctly. We can quite easily validate that because we know the length of the firmware and we know the version number that we're passing in. I think I'm 1, 2, 3, 4, 1, 2, 3, no, there's one more. Okay, so we'll try that. Argument must be read, write bytes like object, not bytes. Yes, because when you read, by default you get bytes, which is read only. We need to convert this to a byte array so that we can write into it. Then object of type int has no length. That's right, we don't take the length of version value, we just pass version value itself. That is not correct. Yes, that's right, because we're not reading the signature here. We are instead reading the entire file there, which is not right. Instead, we should seek to the end. We want to seek to the end. So we want to go minus AES block size, and that should take us to just shy of the end, to the point where we can actually do this. I think this is correct. But now there is a complaint. Unindent not expected. Did I do something kind of strange here? I thought that this was fine. Unexpected indent. Oh. Invalid argument. Okay, I know that there is a way to seek to the end, but I don't remember how we actually do that. F dot we can use tell to get the size of the file. But I'm sure that there's another way of doing this. Okay, we can use tell. That's fine. So that's going to be f.tell. That will give it the size minus 16. Hopefully that should work. Invalid argument. Okay. So we pass in an offset. If I do this, what do we get for that? We get minus 16. So tell is saying that the image is 0. Does that make sense? No. What is tell giving us the size of the file? Is there some... I should just look this up. Python read from end file. To read file in reverse order. It's not quite what I want, but maybe they've got offset. We can seek to the file size is the remaining size. Oh, this is what I'm looking for. This is what I'm looking for. Okay. So instead of doing this, we're going to still go minus 16, but we're going to use os.seek end. Okay, that seems right. Signed firmware version 1. This is the key we're using. And this is the signature that comes out. So let's just take a look to see that the image to be signed, that we're actually injecting the right thing here. So this is our firmware like Sentinel. This is the version number. So hex 42 in little endian, and this is the version number, which is version number 1, and then this is the size of the firmware, which is 156. Is that right? No, I'm reading as a UN8. I should be reading as a UN32. 3484. ls lab of app bin. Yes, that's not telling us anything useful here. I think that's right. We also see that when we do firmware updates, so I think that is correct. 3484. Well, I think that's working correctly, and if that is the case, then that also means that the signature is probably also correct. So if we look at the encrypted image.bin, the last block here is 61ED00, 61ED00, so this is also correct. Great, that is our signature. So the one thing we need to do before we actually, we're going to remove the signing image firmware, we're going to remove the encrypted file name. The one thing we need to do is that now we have this signature, we need to stuff this signature back into the original firmware image. That's the whole kind of main point of it. So the firmware image, the firmware info offset, the signature offset is the firmware info offset plus the 1 AES block size. And now what we want to do is to take our firmware image and we want to inject at a certain point. So we want to inject at the point firmware info offset. No, sorry, we want to do signature offset to signature offset plus AES block size. We want to say that all of that equals the signature. And then finally, we can write out a new signature file, like a signed file. So we'll do we'll do one more right here. And that's just where we're putting all of these file names. Let's put those at the top. We're going to have the signed file name. We'll just call it signed.bin. So this is going to be the signed file name, and that's going to be firmware info image. Okay. Alright, we ran it, we wrote the signed.bin. That gives us the vector table. Then down here we've got our firmware info section that contains now a version number and a firmware length. And we also have our signature injected in, and then of course the code begins. So all of this is looking perfect. Absolutely brilliant. This is the image we can stream in over the firmware update program. Alright, now that we know that, now we can come to the actual implementation of AES. So let's get rid of this comment as well. How many lines of code is this? 69, not bad. I thought it would be a little bit longer. Alright, so let's get to the bootloader part. So I think this is also not going to be as bad as it seems. So what have we got so far? Let's take a look. So if we go to the bootloader.c, we have a whole bunch of things going on in here. We have the validate firmware image. Of course, we've removed some of these, and this part is no longer going to be relevant. So we'll just put a return false in here. And basically, at this point, we're going to do the signature check. So it's going to be the same thing. Let's bring in the AES header. And there's also, while we're here, we're going to need string as well, because one of the things we're going to need to do for this validation process, let's put this here. One of the things we're going to need to do is to use like mem compare and mem copy and a couple of things like that. I don't know if we'll need mem copy, but at least we'll need mem compare. Maybe mem set as well. So let's bring in string for that. And the validation process will be that we need the secret key. All right, let's start with that. So up here, we're going to have a static uint8t, or static const uint8t array of AES block size, which is going to be our secret key. 01, 02, 03. It's going to be annoying to type this out by hand, but 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Alright, not that bad. uint8. Oh yeah, this should be the name. That's uint8. Secret key. Right here in the firmware, just right here in plain text in the firmware, the secret key. So that's, yeah, you can see why that is not the best thing in the world to have, because if someone gets hold of that, all of a sudden they can sign any firmware they want, and your entire security mechanism is down the drain. Of course, you can protect against that. You can try to put things in place, and especially with actually secure ARM chips, like things that have things like trust zone, you can get a lot closer to it, right? But by default, like with this kind of chip, you know, now this is not necessarily the best thing to do. You know, you have been warned, you've been disclaimed. Okay, so we've got our AES key. Great. Block by block, we need to use the AES CBC decrypt process. then we need to decrypt the info section first, which contains the, encrypt. I don't know why we're saying decrypt here. Encrypt. We need to use the encryption process, the same one, because we have plain text. So we're going to encrypt the firmware info section, which contains both the length and the incrementing version number. We're going to ignore the signature section, and then after the final block has been encrypted, we've got the signature. We can mem compare that with the signature that we have stored in the firmware info, and if it doesn't match, then we'll stay in the bootloader. Okay, so first things first, we need to set up a couple of things. We need to get our key schedule, like we need our round keys. So to get those, we need to run we need to run this key schedule function. So we're going to run key schedule, and we need to pass to that a constant AES 128 key. Well, that is already just the const AES 128 key is the is just a UNA array. So we already have that. That's our secret key, and we need a block that's going to represent our set of round keys. So what I'm going to do here is to make an AES block T round keys, and we're going to have AES num, what's the constant here? It's up here. Num round keys 128. Set all of those to 0, but we don't even need to do this. We just need to have memory for that. Then we are going to pass those in, and like all of these functions, they mention here. This one mentions taking a pointer to an AES block, and of course, like what we have here is an array of AES blocks, so this will degrade to a pointer as we put that in. So what we should have is our round keys after this. And then the next step is going to be setting up the state that we're going to have, right? So the state for us is just going to be like a block, and that block is going to, like at every step, we're going to be having, let's actually open up the image. It will be easier to go through with this. So our state is kind of going to be like, it's almost like this block, you can think of it, right? In the image, we're missing an XOR here because we don't have the IV. But you can imagine that our state starts off as kind of the IV. So we always take our plain text, we XOR it with whatever our previous state was, which in our case will be all zeros in the first case. So we'll XOR it with all zeros. Then we plug it into the AES algorithm. And what we get out from that, the kind of modified state, is the first ciphertext block. Now, of course, we don't need to store any of these. We don't need to do anything. We just need to keep a hold of it as we're going through, and eventually we get to our MAC. But in this case, we're going to keep two pieces of state. The thing that we're going to plug in, which will be like the plain text section we're working on, and the previous thing, which will be, in our case, all zeros in the beginning, and then the ciphertext blocks that we get out. All right, so let's make a AES block T, which will contain our state. I'm just going to call it state. We'll set that to all to be zeros in the beginning, and then previous state is also all zeros. That's the IV. Okay, and then we actually do need to deal with the fact now that we need to pad these blocks. So I talked about the fact that there is a standardized padding process. And basically what you do there is you check how many, like you take your size of the thing that you're going to be encrypting, and you work out how far off a full block are you. Like if you take your firmware size mod 16, that will tell you the number of bytes that you need to pad. So what you then do is you take that number of bytes to pad and you plug it into those empty sections as the padding. So if you had 4 bytes left to pad, you put the number 4 times. And when you actually come to decrypt, What you actually do is you just say that my final block should always contain as the final elements the number of like padded blocks. So if you found the number 5 in the very last position of your block, you would check to see that the last 5 bytes were 5, and then you get rid of them, and then you know that the rest of your message begins like that. What do you do if you don't have, if like you happen to have a perfect like on the nose alignment of 16? In that case, you add a whole new block and you put the number 16 in every position, and then you encrypt that. So your last block, if you figure out like, hey, this is all like, it's all 16s, it doesn't make sense, like you throw it away, and then everything else is your actual data. So that's how you can encrypt data that has less, like, is not aligned to a 16-byte block. You can still do it if you follow this mechanism. This is this like almost the standard way of doing it. I don't think there is. I think this is specified somewhere, but it's not specified in the main AES document. But there is basically like, this is how it's done. So if you use OpenSSL, this is the method that it will use for this. So we need to follow that because we're using OpenSSL, but also everyone is doing this. This is the way you do it. Okay, so the number of bytes that we need to pad, bytes to pad, like that is the firmware info length. So we've got our firmware info here that we got from this we've already got that in the previous videos. So we've got the length. We take that and we get it mod 16. This will get converted into just a mask, a bit mask, so we don't need to worry about that. So this is the number of bytes that we're supposed to pad. Sorry, the number of bytes we're supposed to pad is 16 minus this number. And then if bytes to pad is 0, then bytes to pad is actually 16. That's how that works. All right. We need to know that bit of information as well. So now what we're going to have is, let's write a little function, and the job of this function is going to be to kind of perform all of the steps that we need to do as part of this process, right? So what we're going to need to do is to take our input, our state, and XOR it with the previous state in this thing. Then we run the state through AES, and we are going to get back out this part. So we are going to have the process of doing this XOR, running AES, and that's basically it. That's kind of it. Like we're going to end up writing back out to the same state, so that shouldn't be a problem. Yes, okay. All right, yeah, and then of course we need to copy back to the previous state as well. Yeah. Okay, so this is going to be CBC-MAC step. And this will return void, and it will take in an AES block T state and an AES block T previous state. Alright, so the first thing we'll do is we'll XOR these things together. So let's just do for UNAT I equals 0, I is less than AES block size, I plus plus. Then we will take our state, which is a block right now, so it's I think we're going to convert it to a UNAT pointer, cast it to a UNAT pointer, and then we will index it at position I. So we'll say that this XORs with the previous state. This is sort of the most straightforward way of doing this. Well, maybe it's not. I just don't want to have a double nested for loop and loop through like the columns. I'd rather just like treat the thing as a flat piece of memory and just copy one to the other, right? Or rather do this operation like byte-wise on both of these things. So that's the first thing. This is just like this is the CBC chaining operation. This is like what makes CBC CBC. Then we actually run AES encrypt block. So, we actually need to take in the key schedule here as well. So for that, we will take in, and what does this take? It takes a const AES block pointed key schedule. Let's just do the same thing. Let me copy. And let's rename it key schedule. Alright, so we will pass in state and the key schedule. And then finally we need to copy like whatever comes out of state into previous state. So we'll just do that with a memcopy. Memcopy. This is our destination, then we have the source. So the destination is previous, source is state, and the size is AES block size. Good. Alright, so this is a step of the algorithm. So we're getting close here. So basically we're gonna have done a certain number of we're going to have done this. This is going to be our offset. Offset will start at 0. And while our offset is less than the firmware info length, so we're going to be going through the whole length of the firmware. And offset will actually start after the signature. So we'll do this in we need to do like a manual first step. So the first thing we're going to do is to do the firmware info section. So let's do memcopy. Memcopy, we're going to be copying into the state, and we are going to be copying from this address. So we can actually just pass in firmware info to this, right? Firmware info, and the size is AES block size. So we're copying this block in, then we are going to run AES CBC-MAC step on the state, the previous state, and the key schedule, which is our round keys. Alright, so we run this part, and then we're just going to move on to the next part. So this is the part we can do in a loop. No, that's not really true, is it? We kind of need to do 2 loops. Or we recognize when we're in like the point of this point and we just skip it. Could also do that. It's a little bit ugly, but yeah, maybe I'll just do that instead. I think that's kind of like, it feels less hacky somehow. So we can check if the offset, if it's equal to the, this is not too bad, right? Although we need to subtract the flash bait. Yeah, but actually we always need to take this from that. Yeah, you know what? So if it's equal to the firmware main app start address minus the firmware info address, we just look like this is flash-based bootloader size. That puts you at the main app. And main app start minus this, so no, it should be the other way around. So firmware info minus the main app. That's going to get us to the offset of being at this firmware info. In that case, we'll just say that the offset plus equals AES block size times 2, because we're skipping 2 blocks here. We're skipping the firmware info and the signature block. Then we will continue. Okay, so that just takes care of the point where we need to skip the info and signature signature sections. Okay, and now we can actually check like just the main part. So the main part here is the first thing we're going to always need to do is check, are we at the very last block? Because the last block we will need to pad it. So let's check. Are we at the last block? So if the current offset that we have right now, wait, let's do it like this. If the firmware info length minus the current offset, if it is greater than the AES block size, yeah, it has to be greater than 16. If we had 16 bytes left, then that would we'd also have to do padding at that point. That's when we'd have to pad a final, like a final amount onto the thing. So if it's greater than AES block size, this is just the regular case. Otherwise, this is the irregular case. The case of padding. Yeah. Alright, so in the regular case, we basically call this function. That's it. No, we do need to first do the mem copy from the main app start address. We need to cast this to a pointer. So this is going to be a void pointer. Main app start address plus offset. That's the destination. This is the source. So the destination is state this is the thing, and then AES block size. Right. So we copy in the thing we need to deal with, and then we do a round. That's it. In the case of padding, we need to check, like, is this we need to check for the special case, which is do we have 16 bytes, right? I'm sure you could write this code more elegantly, by the way. You could take out like this special casing, but in fact, we always need to do this, so we might just want to put this at the end after all of this stuff. Well, let's see. Okay, in the special case, if the bytes to pad is 16, this is when this whole block is fine. We need to just do a regular block, and then we need to pad it and do a block of padding. So in that case, we also do this. But then afterwards, we're going to, after we do this part, then we will memset state to we'll memset state to 0. No. We'll memset state to bytes to pad, basically. And we'll do that for the whole block. And then we'll do one more round of this. And then we're actually done with that. Otherwise, this is the, like, so this is the add a whole extra block of padding. And now we need the case where we just have just a couple of bytes to be padded. So what we want to do here is then memset, we want to mem copy from our offset, and we are going to only mem copy like the rest of the bytes that we actually have. Like we only do AES block size minus the bytes that we're going to pad, and then we can do a memset, like same as this part, where we're going to memset into state, but we want to let's cast state to avoid pointer, because I want to add to it, what's this going to be? It's going to be 16 minus the number of bytes to pad, or rather, sorry, AES block size minus bytes to pad. And then we are going to pad the bytes to pad value and for that number of bytes. Yeah, in that case we're just doing the whole section here. And I'm just wondering now, yeah, let's leave it like this. This part, if this was 16, we would then pad the whole state. So this would be 16 minus 16 would be 0, so we would pad at state for 16 bytes, 16. I'm just thinking, like, can I get rid of this and then we just do these steps afterwards? Probably we can, actually. The memset part. I'm wondering if I can do this. And not even that, but just this as well. So this would be that we add the block of padding in this case. So like we just make sure it's padded, and then in this case we like make sure that the state contains as much information as we have for that part. And then in this part we would memset the bytes to pad. If we came from here, we would not pad anything. This would end up being a zero operation. Memset, if you pass 0 to memset, is that valid? I need to check that. No, this doesn't work. Let's not do it like this. Let's do this the stupid way, which is put those back in, and we'll do this operation like that. And then at the end of having done this whole operation, offset will be increased by AES block size. I think that's right. So what are we doing here? We're first going to encode the firmware info with 0 as the previous state. Then we're going to do everything else. So we're going to skip those sections if they come along. But otherwise, we're going to basically check that we have just a regular number of blocks like left. We've got like more than 16 bytes available to encode. If we do, we will copy from the flash at that offset into the state of an AES block size. We will run the encryption on that. And then if it's an unusual case where we need to do the padding, well, we'll check, like, do we have an even number of bytes? Like, we don't have this condition right now, so this isn't going to happen in this code, but it could happen in the future. In this case, we will first just do a regular old version of this, where we just copy the current offset into the state and then run the encryption on it. But after that, we will then set the whole state to be 16, like explicitly. Just, I think even let's be more explicit about this, right? This is we can just do away with that. And then we run one more of that, and then this would be our ending condition. Both of these actually are our ending condition. Otherwise, we're going to copy as many bytes as we can that we have left into the state, and then we're going to set the rest of those bytes to be whatever bytes to pad is, and then we'll actually run that one here. Okay, and then we're adding to the offset, so eventually what should happen is that our offset will be equal to or greater than the firmware length, right? We will have skipped past it. So then we'll be done, and then we will compare the signature section. So the signature, so we can get the signature by saying const UNAT signature. I guess this is just a pointer to a signature, and that is the just cast the idea of the signature address, which we should have here. Alright, so then in the end, what we return from this whole operation is mem compare, and we're just going to pass in two pointers here. So one of them is the signature itself, the other one is the current state, and the size that we're comparing is an AES block size, and if these two things match, then that actually means that the thing was successful. Okay, I think that's it. So let's try it out. And basically, if this fails, then we're going to need to dig in a bit. But actually, we're going to need to first do a firmware update. So we're going to need to do and actually we need to fix that first. So that's the final part, the firmware updater. Let's close this down for now. So what do we do here? We already changed the offset of the vector table, but in fact we don't need to do any of this stuff anymore because we don't need to interact with the firmware info section. No, that's not true. We do need to interact with it because we need to extract the length and the device ID, but we don't need the version. We don't need to validate. And the firmware info size, do we use that somewhere? Yeah, we're using that in the CRCs, but we don't need that either. So let's come down to this part. So we're going to read the image now, and instead of reading an explicit image, let's read that from arguments as well. We don't need to slice off the bootloader anymore. We don't need to inject any information, so we'll get rid of that part. So before we do this, let's read the argument. So we're going to say if process.argv.length is less than, and what we're going to pass in here is just the firmware image. So this is going to be less than 3. Then we will console.log usage firmware updater .ts, well, the firmware updater signed firmware, and then process.exit. And now we are going to sync with the bootloader, request a firmware update, do all of these things. We're still going to get the device ID from the same place, encode it. Yeah, I think actually that's the only change we really need to make here. So let's try this out. So right now, the device is sitting on my desk, UART's plugged in, and the light is blinking, right? Just because we're in the same state that we were in the previous episode where we had the integrity check going on. So now let's actually do the signed firmware check. So let's run the bootloader. Am I running the bootloader or am I running the main application now? I'm running the main application, which actually is going to fail at this point. So, okay, there's a couple of things. So, AES tries to get a file called common, which we don't have. We have something called common defines, and it's looking for the same thing. It's looking for like the UNA and that kind of stuff. But also we do need to put this into the make file. So that's the next error we would have gotten. Make file, and that's just going to be source directory AES. All right. Okay. So there are some things here. So let's take a look first. It's telling us that there is a shadowed state, and that's true. Yeah, we've got a variable called state here, so let's get rid of that, because that's no good. Let's call this AES state. Okay, and we're going to want to do the same thing here, and anywhere we use state, which will be here as well, here, 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 and here. All right. Let's see if we get rid of those warnings now. Good, no warnings. Let's get the firmware update program on the go. So this is going to be Python firmware signer. We don't need to sign anymore. We can actually run actually have the signed firmware. So ts node firmware -updater, and then we're going to pass in our signed bin. So let's run that already. Oh, the port is not open. That's interesting. Let me take out the UART there, plug it back in. Port is not open. No, this is the same thing actually. This is the same problem I had before, which is that we're getting some error probably at some other point. Let's just remove the finally here and see what the actual error is. No such file, firmware bin. Yeah, of course, because we're trying to get the firmware file name, which will be process argv2, and we're going to pass that to this. Yep, okay. Get rid of this, and so is the run. Yeah, I probably should have let that run. Okay, so we're gonna get to the point where we're erasing. We wrote all of those bytes, and then here we've gotten to the end here, so we're about to do the mem compare. and I cannot believe that that worked first time. No way. Okay, I'm gonna... Oh wow, that is like... I'm so proud of myself for that. Like, I just made sure that the firmware update of all the bugs that I've had in this series. Unbelievable. Okay, so for the very last time in this series, I'm going to hold up a board with a flashing LED on it and tell you that that means... Oh my gosh. And tell you that that means that we did in fact succeed in our goal of updating a properly signed firmware. That is amazing. I'm incredibly happy with that. So now let's actually set this up in a failing condition. Let's flip one bit somewhere and make sure that this will not work. Or try and sign it with a key that is invalid. So I've pulled out the I've of course pulled out the UART wires now, so I need to plug those back in. Alright, let's try this again. So in order to mess this up, let's just open up this in hex editor. Open hex editor and let's change something in the signature. We could do two things, right? We could change either a signature or we could change like any byte in this firmware image. So let's just change something in the signature or in the firmware info, right? Let's say that it has, instead of being version 1, that it's version 2. Let's save that. And now we'll run the firmware thing again. So I'm just going to start debugging. We'll run that, run this one. So we're going to write a firmware update, and that's complete. And this time, oh, I know what the issue is here. Actually, I know what the issue is, and this is this is not the good news I thought it was. Okay. It does mean that we got another kind of bug somewhere, but we can work it out. Okay, so mem compare, the output of this is an integer, and you actually have to check that it's equal to 0 for this to be true. So in this case, this would be a part like, this would actually now should not jump to the firmware. So if we run this again, and now the firmware's burned on, so we can just let it wait the 5 seconds so we can get down to this point, and then if we do this now it should fail, and it does. It stays in the firmware. So what we can do is to, and of course we get here again, so let's go into this signed thing, not in a text editor, open in a hex editor, and let's flip that version 1 back, because this is how it should be, and we can get ready to run this again. Alright, so at this point it looks like it's going to fail again, and it does. So we need to try to figure out what's going on here. So the first thing I think is quite useful to do is to just, what's the easiest thing to do at this point? I just want to log out the first like output of running the AES CBC-MAC step. So let's see if there's a problem at this point, because maybe there is. And what we can actually do here, I think, is to set a log point and just print out the previous state. I think that's the... Is that the simplest way? It could be. Just let it run. Maybe we can actually use the memory viewer here to do this instead. Okay, so let's use the memory viewer, and we'll add a memory view, and we'll be looking at the previous state. All right, this is, can we just see the address that it's at here? Well, no, apparently, but in the local state, AS state, previous state, yeah, it's not going to show the address, but I think if this is it, then this should be like, this should be the first thing that we see. Yeah, okay, so state and the thing, they're both equivalent, they're both set to the same value. So I believe that this should be what we would find if we went to look up, oh no, they're not set to the same thing. They diverge at this point. But this one should be 16 bytes. So this should be what we look at if we look at the, and of course we're deleting those files now. So we need to run the Python signing program again. Python, so we're going to sign the firmware, and also we need to not remove those files. This is why it's nice to like not put this in like temporary directory straight away, because it is really useful to be able to look at the intermediate file. So we want to look at the encrypted image, and so what we should expect to see is like this, these values here, 56, 8B, we would expect that that would be the first row of things here, and it's not, so there is an issue going on. So what is the issue? That's the main question here. Let's take a look at the previous state. Well, let's put another breakpoint down first. Let's just make sure that this way of even doing this makes sense. And let's preview some of the other variables as well to make sure it seems to be making sense. So bytes to pad, we know that that should be 4, right? Because we saw that there were 4 padding bytes. Instead it's 16. So yeah, that's already an issue here. But that's not the issue, because we didn't see the right output on the first thing here. There's definitely one problem that we would have had there. Okay, so this time around bytes to pad should be 4. It is, that's good. And I actually wanted to check I wanted to check that here. Let's wait 5 seconds. And let's go to this memory view here. Now the memory view is not working. Okay. It was working. Now we can't do that for some reason. All right. Yeah, we can always do this. This is also why I wanted to do this, like, just trying to put some breakpoints in to prevent it from running away. But maybe what we can do is to so I want to just print out hex 02x 16 times. And then we've got this, what's this? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is going to be prev state. And then run everything on this line. It's going to be part of so let's log this long term out here. So let's add a log point, and we'll be logging this stuff. This is not going to work because we need to all of these prev states, they need to be cast to a UART pointer first. So let's find all of those, and we'll do it like UART pointer. Okay. Now I think we should be able to log those out. So let's do that. Debug console, did it log? Yeah, okay, all of those are 0. That's correct. Can we now take that and put it here? Same thing. Alright, yeah, that's true, we did put that there. Okay, so now we get 2E, E2, and I don't remember if that's what we saw here. This is in the signed, no, that's the signed firmware, we need the encrypted image. 2E, E2, 85, great, that actually is perfect. So you know what? Let's log all of these. Let's borrow that, and let's make sure that every time we hit this offset statement that we do this as well. We're always going to copy the previous state in, so we can look at the previous state as our state, right? It's going to do the same thing at this point. So let's let that run. So we can take that out. Alright, you can see that there's a whole bunch of information coming out here. So the encrypted image, 61ED. Ah, so maybe we actually did solve it with this padding problem. What do you know? We're jumping to the main. That's it. We are signing the firmware and uploading it to the device and having that be guarded here by this statement. I almost can't. Yeah, I knew that there would be at least one bug. I'm almost glad that there was a bug here because I just didn't trust it when it was working correctly first time around. That was sus. I'm so happy with this. Like, this is such a good result, I think. And I think it's also a fairly clean implementation, right? This bootloader file is getting quite large and substantial now, and it's doing quite a lot of different things. So, I mean, if this was me, I would probably start to split this file out a little bit. Some of the responsibilities, I would maybe put all of the signing related stuff and the validation, put that just in a different file. Maybe I would put the bootloader state machine in its own file, kind of break that up a little bit. But for all intents and purposes, we've hit the goal here. We've actually implemented cryptography such that we can do firmware updates over the USB port. So imagine now we've got a device. We put this on a printed circuit board. We take the chip, we put it on a printed circuit board, and we take the chip that's on the USB to the UART adapter. We put that on a circuit board as well. We put a little USB port on it. And we say that to our users that they can update the firmware if they plug it in and run this piece of code. And of course, we wouldn't want to, show all of those lines of debug. We probably wouldn't want to write the thing in TypeScript if we were going to have this as a firmware update mechanism. But you can imagine we could also do this in a web browser, right? You can use Google Chrome with Web USB, even Web Serial, right? You can use just the Chrome browser to do all of this firmware update mechanism just in the browser. Like, that's how straightforward this could be. And yeah, and at this point, if you turned off the debug interface, if you turned off the ability to dump the flash, which are things that we should look into, if you do those things, then it actually becomes feasible that you have this like authenticated firmware update mechanism that no one else can touch, right? They have to go through your signing process in order to get there. I'm incredibly happy with this result. I hope you've learned something from this series. For me, this has been like a fun learning experience to delve into topics and validate that I understand them enough to explain them to you. Maybe I've failed or succeeded on those. That's kind of in the eye of the beholder. But I'm really happy with it. I think that, you know, this should add to the content out there on YouTube and on other platforms about this subject. I think there's a lot of dry material, and I hope that I've managed to make some of this like less dry than it would be in other cases, and I hope that you've been able to kind of get something that you wouldn't be able to find in other places as well. In the future, I want to go a bit further with this, and I have a device that's been sitting in my drawer for a little while, and it is this. It's a chip whisperer light, and this is a board that's made by Colin O'Flynn, who is a security researcher, and he has basically put together this chip whisperer board, various chip whisperers in fact, and they all revolve around fault injection and power analysis and all kinds of like ways of trying to exploit weaknesses in chips, just like the one that we have here, and to be able to do things that break assumptions about algorithms like AES and RSA in order to extract secrets and secret keys. So what I would really like to do is first learn how to use this board and then try to attack our implementation, try to attack this AES implementation and see if we can't extract the key without, you know, having prior knowledge of it. That would be really, really cool, I think, and I would love to document that journey here with you. If some of you find that interesting, if you find that the idea of that interesting, let me know in the comments. You can also join the Discord server. I would love to talk to you about what you thought of the series, what your own projects are, and how you've maybe adapted this, tried something else. I'm really genuinely interested. So if you've got something to say about it, please let me know. I think that is kind of all for now. And I really appreciate you taking the time to watch these videos. I know they're long. I know they're quite information dense, but you must be one of the other nerds like me that like this kind of thing. So in the end, I'm doing this for you. I hope you're enjoying the content. All right. Thank you for watching. I'll see you next time.